Next, we will discuss the toroidal inductor. First point, how it works. Wire wound around a ring-shaped magnetic core. The closed magnetic path prevents leakage flux, making them very efficient and EMI resistant. This means the coil is wrapped around a donut-shaped core, which guides the magnetic field. The core forms a continuous loop. Almost all magnetic field lines stay inside it, reducing energy loss. Minimal flux leakage means the inductor wastes less energy and causes less electromagnetic interference to nearby circuits. Next, why it's used. High efficiency. This means most of the magnetic field is contained inside the core, so very little energy is lost. Low electromagnetic interference. This means the closed magnetic path reduces stray magnetic fields, minimizing interference with nearby circuits. Compact for high inductance values. This means they can provide a storing inductance in a small space, saving design. Next, we will discuss the drawbacks of toroidal inductor. More difficulty to wind. This means the wire must be carefully wound around the ring, which can be tricky compared to straight or solenoid coils. Custom manufacturing may be needed for special values. This means if you need a specific inductance that isn't standard, it may require custom design and production, which can be costly. Next, we will discuss the real life examples of toroidal inductors. Audio crossover networks. This means separate high and low frequencies in speakers for better sound quality. Solar inverter circuits. It helps convert DC from solar panels to AC efficiently. Power factor correction circuits. It means improve efficiency in electrical power systems by reducing wasted energy. This image shows the toroidal inductor and its symbol. Left side 3D view shows the actual toroidal inductor with copper wire wound around a ring-shaped magnetic core, means donut-shaped. The wire loops around the core multiple times to create inductance. The core concentrates the magnetic field, reducing leakage and increasing efficiency. Right side schematic symbol represents a toroidal inductor in a circuit diagram. The two lines coming out are the connection terminals. The circular loop symbolizes the ring-shaped core and winding. We will discuss the laminated core inductor. First point, how it works. Made from stacked EI-shaped silicon steel laminations to form a core, reducing eddy currents. The coil is wound on a bobbin that fits between the E and I sections. In simple explanation, made from stacked EI-shaped silicon steel laminations. It means EI shape means each lamination looks like the letters E and I. Stacking means multiple E and I laminations are stacked together to form a complete core. Material like silicon steel is used because it has high magnetic permeability and low electrical conductivity, which helps reduce energy loss. Reduce eddy currents. It means eddy currents, these are loops of current induced inside a conductor when it is exposed to a changing magnetic field. By using thin laminations instead of a solid core, eddy currents are restricted to each thin layer, minimizing eddy energy losses. The final explanation: a laminated EI core inductor uses stacked EI shaped silicon steel sheets to form the core. The lamination reduces eddy current losses and the coil is wound on a bobbin that fits between the E and I pieces for efficient operation. Next, why it's used. Handles high power at low frequency. It means laminated cores can carry large currents and high magnetic flux without saturating easily. Suitable for low frequency applications like audio amplifiers or power transformers. Reduced core losses due to lamination. It means laminating the core, stacking thin sheets of steel with insulation reduces eddy current losses. Next, we will discuss the drawbacks of laminated core inductor. Not efficient at high frequency. It means laminated cores are mainly made of silicon steel, which has higher core losses at high frequencies. They are unsuitable for RF circuits or high frequency switching applications because they heat up and waste energy. Bulky and heavy. It means to handle high power and reduce losses. Laminated cores require thick or large stacks of steel sheets. This makes the component physically large and heavy, which is a disadvantage in compact electronic devices. Next, we will discuss the real life examples of laminated core inductors. Tube amplifier chokes. It means used in audio tube amplifiers to smooth the DC supply. Handles high current at low frequencies without excessive losses. Power supply chokes for industrial machines. It means in large industrial power supplies, laminated core chokes filter current and reduce ripple. Can handle high power levels efficiently. Large AC filter circuits. It means used in AC mains filtering to suppress noise and stabilize voltage. Suitable for low frequency applications where high inductance is required. The image shows a laminated core inductor and its schematic symbol. Left side laminated core inductor. This type of inductor uses a core made of thin insulated steel sheets of ferromagnetic material, typically iron. Lamination helps reduce eddy currents, which are circulating currents induced in the core by the changing magnetic field, thereby minimizing energy losses and improving efficiency. The symbol shown on the right represents an laminated core inductor in circuit diagrams, typically depicted as a coiled wire. The specific symbol shown with the solid lines above and below the coil indicates a core inductor, often a laminated core or iron core inductor. Next, we will discuss the variable inductor. First point, how it works. The inductance can be adjusted by moving a core in or out of the coil or by changing the number of active turns via a tap. In simple explanation, adjustable inductance means the inductance value can be changed as needed. Moving the core means sliding a magnetic core, ferrite or iron, into or out of the coil changes the magnetic field strength, thus changing inductance. Changing coil turns means using a tap on the winding allows you to change the number of active turns in the circuit, altering inductance. Fine tuning means often used in circuits where exact inductance is critical, such as in radio tuning. Next, why it's used. Allows fine tuning of circuits. It means variable inductors let you precisely adjust inductance to match the exact requirements of a circuit. This ensures maximum performance, especially in sensitive electronic systems. Useful in radio frequency applications. It means in radio frequency circuits, even small changes in inductance can greatly affect signal tuning. Variable inductors allow accurate adjustment for clear signal reception or transmission. Ideal for experimental setups. It means in testing or prototype circuits, component values often need to be tweaked. A variable inductor provides flexibility without needing to replace parts. Next, we will discuss the drawbacks of variable inductor. More complex design. It means requires additional mechanical parts per adjustment, making it more complicated than fixed inductors. This can slightly increase size, cost, and assembly time. Mechanical movement can wear out. It means moving the core or adjustment mechanism repeatedly can cause wear over time. This may lead to reduced accuracy or failure if not maintained properly. Next, we will discuss the real-life examples of variable inductors. Radio frequency tuners in communication equipment. It means used in radios, TV sets, and transceivers to fine-tune the frequency of received or transmitted signals. The inductance can be adjusted to precisely match the desired frequency band per clear reception. Antenna matching networks. It means helps match the impedance of the antenna to the transmitter or receiver for maximum power transfer. The variable inductor allows tuning for different frequencies or changing environmental conditions. Oscillator frequency adjustments. It means in LC oscillators, changing the inductance shifts the oscillation frequency. Useful in signal generators, radio frequency circuits, and testing equipment to obtain accurate frequencies. This image displays a variable inductor, also known as the tunable inductor. A variable inductor allows for the adjustment of its inductance value, typically by moving a magnetic core or slug within the coil or by changing the number of turns in the coil. Left side image shows a common type of variable inductor where a threaded magnetic core can be screwed in or out of the coil to alter the inductance. Right side image represents the symmetric symbol for a variable inductor, which is a standard inductor symbol with an arrow passing through it. Thank you very much for taking the time to watch this video.
Padmam Himam